So let's look at the following example. A certain spring stretches 0.2 meters when a 0.4 kilogram mass is attached to that spring vertically. Now we then set up the spring horizontally with the same exact mass resting on a frictionless table. The mass is pushed so that the spring compresses a distance of 0.12 meters and is then released. Assuming that our object is oscillating under simple harmonic motion, we want to calculate in part A the spring stiffness constant and the angular frequency. In part B, we want to find the maximum velocity and maximum acceleration. And in part C, we want to find the frequency and period of our oscillation. So let's begin with part A. So how exactly would we go about calculating our spring stiffness constant K? Well, notice in the first part of our problem, we're given that we take a spring, we place a mass that has this quantity of mass onto our spring, and that spring stretches a distance of 0.2 meters. Now, when that spring stretches, our object is in static equilibrium. So that means all the forces acting on our object sum up to 0. So notice we have two forces acting on the mass. We have the force of gravity m times g, and we have the restoring force due to our spring k times x. So because the object is in static equilibrium, m times g is equal to k times x. So since we want to find what k is, we simply bring x to the left side and we get the following result. Our spring stiffness constant of this particular spring is equal to mass times g divided by our displacement. So the mass is given to be 0.4 kilograms, the g is 9.8 meters per second squared, and our displacement is 0.2 meters. So we plug those values into our calculator and we get 19.6 newtons per meter is the spring stiffness constant. Now we want to find the angular frequency. So angular frequency is related to the spring stiffness constant by the following equation. The square of our angular frequency is equal to the ratio of the spring stiffness constant to the mass. So we take the square root of both sides and we get the following equation. So our angular frequency, which is what we want to find, is equal to the square root of k divided by m. So k we found is 19.6 newtons per meter and m is 0.4 kilograms. So we take the square root and we get 7 radians per second is the angular frequency of our oscillating object that is experiencing SHM, or simple harmonic motion. So what about part B? How exactly would we go about calculating the maximum velocity and maximum acceleration? Well, notice that we're giving the amplitude of our oscillation. The amplitude is simply the maximum distance that we compress our spring, which is 0.12 meters. So this quantity is the amplitude. Now, knowing the amplitude and knowing our angular frequency, we can calculate our Vmax, the maximum velocity, and Amax, our maximum acceleration. So Vmax is given by simply taking the product of the amplitude and the angular frequency. So 0.12 meters, our amplitude, multiplied by our angular frequency, which we obtain in part A, and we get 0.84 meters per second is the maximum velocity reached by our oscillating object. Now what about our Amax? Well, Amax is given by taking the product of the amplitude and the square of our angular frequency. So we take our 0.12 meters and multiply it by 7 rads per second squared, so 49 multiplied by 0.12, and we get 5.88 meters per second is the maximum acceleration that is achieved by our oscillating object. And finally, in part C, we want to calculate the frequency and the period of our oscillation. Now recall the following formula. our angular frequency of the object is equal to 2 pi of the actual frequency. So that means if we take that equation and rearrange and solve for the frequency f, we get the following result. F, our frequency, is equal to the angular frequency divided by 2 pi. So we know that the angular frequency is 7 radians per second. Divide that by 2 pi and we get approximately 1.11 hertz. Now to find the period, we simply take our f and we find 1 divided by f, because the period is equal to 1 divided by f. So we plug in our 1.11 hertz into our denominator and we get approximately 0.9 seconds is the period. In other words, it takes 0.9 seconds for our object to complete one entire cycle, to complete one entire oscillation.